So we said there are three cases, right? One is the Prandtl number is almost equal to 1. The other is Prandtl number much less than 1. We investigate those two. And then the third one is Prandtl number is much larger than 1. So we're going to actually look for that case and what kind of information can we get with this assumption. Now, this hydrodynamic boundary and the thermal boundary, and the thermal boundary is much smaller than the hydrodynamic boundary, as you can see. And this is the region or the domain for analysis for thermal boundary layer equations. Now, we're going to write down the X momentum equation. X. So this is basically Vx. And Vy del T over del Y is equal to alpha del squared T over del Y squared. And let's do the scaling analysis once again for this particular case. And this time Vx, look at here. So this is the region that we want to study, right? What does it mean? It means that we are actually dealing with these velocities, right? So the Vx is going to scale with V delta T. I mean, whatever the velocity is at this point, the velocity is in the range of that one instead of this velocity. We should be particularly interested in this velocity. And that's the difference between the previous case and this case. Times delta T over L. And then this scales with V Y delta T over delta T over delta T. And this one scales with alpha delta T over delta T squared. Okay. And again, to make sense of this thing, we should stick to the continuity equation. Tells us del Vx over del X plus del Vy over del Y is 0. This is in the order of Vx delta T divided by L, and this is in the order of Vy delta T over delta T. So instead of Vy delta T over delta T, you can write it V delta T over L, right? So what we can do is basically this one combined with this fact is V delta T over L. Basically, this and this are in the same order of magnitude, so it looks okay, right? And what about the V delta T? So can I get an idea about V delta T? Meaning that, what is this V delta T with respect to this V delta or V infinity, in other words? So how can I relate the two? So I can make a really rough order of magnitude estimation. get an idea about V delta t, we do another order of magnitude assumption. So you can say, or whatever this V delta t is, if you divide it by this V infinity, you should get something in the order of delta t over delta. Basically, like, geometrically, you can think of it like V is like, this is V delta, sorry, V delta t, and this is V infinity. So you can actually make this scaling if you use the geometry. So they are going to be in the same order of, sorry, if you scale it, this is going to be in the same order of magnitude as this one. I'm not saying that they're equal to each other. I'm just saying that one is 10, the other cannot be 1,000. The other can be maybe 20 or maybe 30 or maybe 50. That's what I mean. Okay. And so that's it. So what do we get for the advection terms? Thus, or the left-hand side of the heat equation. Advection terms gives us this, right? V delta t over L. That's going to be in the order of, using this relation, V infinity delta t over delta L, right? And the conduction terms, the term on the right-hand side, is this alpha delta t over delta t squared. Thus, since advection is in the same order of magnitude as conduction, you get V infinity delta t divided by delta times L is in the same order of magnitude as alpha delta t over delta t squared. Okay. From here, you get delta t cube on one side, right? And let's divide it by L cube. And that's going to be in the order of alpha, the delta t's cancel. And let's divide both sides by L squared to get the L cube on the left-hand side. And you have delta over L squared V infinity. Yeah, I guess, yeah, alpha delta divided by L squared V infinity. Yep. Okay. So what does it tell us? Okay, let's elaborate more on this. So there are things that we know, right? For example, delta over L, we have an idea about it. Alpha over L V infinity. So delta over L, we know about it. Or maybe you can say, okay, so yeah, let's have this delta over L on the right hand side. And the delta over L, you know that, scales with Reynolds number L to the power of -1/2, right? We have seen this before. Thus, delta T cube over L cube is in the same order of magnitude as alpha over E infinity L, Reynolds number L to the power 1/2, -1/2, right? And again, this looks like the Reynolds number, but we need to multiply and divide by nu, right? So you can say, you can do the same trick as we did before, nu over V infinity L, alpha over nu, Reynolds number L, -1/2. Now it starts to look like something, right? This is 1 over Reynolds number L. This one, oops, this one. And this one is Prandtl number. It's basically Prandtl number to the power -1, right? Because it's nu over alpha, which is Prandtl number. And then you have Reynolds number L, -1/2. Now we can simplify this and this. Oops. Right? So we get Prandtl number to the power -1, Reynolds number L to the power -3/2, correct? If you add -1 to -1/2, you get -3/2. Okay, now, long story short, you have this delta T cube over delta, over L cube. But if you want to get the delta T over L, instead of the cube of it, that's going to scale with 1/3 power of the right hand side, which is Prandtl number -1/3 times Reynolds number L to the power 1/2. Awesome. What a beautiful relationship, right? But still, we desperately need the Nusselt number, not the delta T, right? The delta T is just a means for us to calculate the Nusselt number. So let's relate the Nusselt number that we desire for. So that is HL, that's Nusselt number L, divided by K fluid. That's equal to, as we did the trick before, H delta T over KF why am I okay? Good. L over delta T. Now I know the L over delta T over L, or in other words, L over delta T, right? I can write it there if I like, but yeah, let's have a look at this thing. So what about this? So I know this thing can be Prandtl number 1/3 times Reynolds number L 1/2. But what about this? Right? So let's try to figure it out. Now we can write down again the same equation as we did before. Minus K fluid del T over del Y at the wall, Y is equal to 0, is equal to the convection H T wall minus T infinity. And then do the scaling analysis. This scales with K delta T over delta t, right, is equal to, or not equal to, and this scales with h delta t over nothing here. Okay. And then from here, we get h times delta t over k fluid. Yeah, the delta t's cancel. Is in the order of 1, or scaling with 1. Okay. Good. Okay. So, bingo. So we got this thing, right? So our Nusselt number, L, is gonna scale with this thing, right? Because this scales with 1. L over delta t. And the L over delta t, as we said before, here, scales with Reynolds number L to the power 1 second, Prandtl number to the power 1/3. Right? Okay, cool. Good. So let's write it. Nusselt number L is Reynolds number L second, Prandtl number 1/3. What was the result from the previous one? It was Prandtl number 1 second, Reynolds number to the 1 second, but this time the Prandtl number is 1/3 instead of 1 second. Oh, the dependency to Prandtl number is changing. So that's a very important scientific insight. We say that Reynolds number dependence is the same as the case where nu over alpha is much less than 1, right? The previous case, case 2. Okay, cool. So we have found the relations for the Prandtl number, sorry, for the Nusselt number for 2 cases, for 3 cases. Let me actually have a look at this thing. For Prandtl number almost 1, the Nusselt number was scaling with Reynolds times Prandtl, right? As you can see here. Okay, good. Okay, so let's say page. Any questions so far? You don't have any questions, so let's move on to the next thing. Now, what have we done in the momentum boundary layer theory? We first got just order of magnitude estimations. We just had a sense of the boundary layer thickness and so on, but then we used the integral method, von Karman integral method, to get some exact solutions if you remember, right? So let's go back to this one. We did this analysis and we got we solved for actually both the delta, right? We found the boundary layer thickness as a function of x. So we're going to do a similar thing to calculate this for the thermal boundary layer. Oh no, I did, oh, page 4, no, I don't have page 4 here. So let's delete it. Okay. Let's have page 3 here. Okay, good. So do you need a summary here? Let's do a summary here. Summary. We investigated three cases. Prandtl number, almost 1. Where we got it was yesterday, I guess. Nusselt or Reynolds-Prandtl. CF/2. For Prandtl number much less than 1, we got the Nusselt number scaling with Reynolds number to the power 1 second, Prandtl number to the power 1 second, and 3, for Prandtl number much larger than 1, Nusselt number, Reynolds number 1 second, Prandtl number 1/3. So these are the from the order of magnitude estimations. Now what we are going to do now is we're going to try to solve the equations. Okay, now let's say integral method for thermal boundary layer analysis. Okay. Now, let's take a look at the thermal boundary layer equation. Okay. Which was Vx del T over del X plus Vy del T over del Y is equal to alpha del squared T over del Y squared, and integrated over the boundary layer thickness. Delta T. So we get 0 delta T, Vx del T over del X, dy, I'm integrating over the y direction, plus integral from 0 to delta t, Vy del t over del y dy. And let me not do any particular assumption yet. Okay, is equal to alpha del 0 to delta t del squared t over del y squared dy. So since this is very similar to the velocity equation, we can use exactly the same tricks that we used for the momentum transport, right? So we can actually, we have strong belief that this integral method is going to work just because we know that it works for the momentum case. This piece, let's integrate by parts. Okay, here we rewrite it. 0 to delta t. Vy del t over del y dy is equal to, it's like udv. We're going to have uv, which is Vy t from 0 to delta t minus integral v du t times del Vy over del y dy 0 to delta t, right? This term we can write Vy at delta t and the temperature at delta t. The temperature at delta t is nothing but T infinity, right? Minus Vy at 0 is 0, so it makes at 0. We can cancel it. Minus from 0 to delta t, t del Vy over del y dy. Okay. Good. From the continuity equation, you can actually get an idea about this term. Del Vy over del y is nothing but negative of the del Vx over del x, right? Thus, the term that we integrated by parts becomes equal to minus minus makes plus, this minus and this minus, t del Vx over del x dy from 0 to delta t. Now the thermal energy equation becomes, let's have a look at it, integral Ex del t over del x, Ex del t over del x dy, right, plus Vy delta t, t infinity plus integral 0 to delta t, t del Vx over del x dy is equal to alpha integral from 0 to delta t It's basically d, del t over del y. Right. I mean, if this step is not clear, just let me know. I can explain.
Yeah, can you explain it just?
Sure. So the right-hand side here becomes 0 delta t, del over del y, del t over del y, dy, correct? And this del y and this del y cancel, right? And so you get del 0 to delta t, del t over del y. It's like you're integrating, it's like integral dx. Okay. And okay, is that clear?
Yeah, that's clear, but it's just because you have regular d, like not del.
Yeah, because x is not changing, it doesn't matter. I'm integrating over the y-axis, so it's, I mean, it should not be ambiguous. So
Okay.
you can make it del, that it doesn't matter. Okay, because I'm integrating over the y-axis without changing the x. Okay. You can combine some of the terms here. For example, this term and this term, because you have the same dy there. Ex del t over del x plus t del Ex over del x. Oh, what is that? It looks like something familiar, right? And I write this too. Vy delta t infinity is equal to alpha okay. And this one, as you know, is the chain, it's the product rule, right? It's the derivative of the multiplication of Vx and t. Right? Okay. So you can write in a more compact form. By delta t infinity is equal to alpha now. Let's write down this Vy delta t. Let's elaborate on that. Let us get Vy delta t from integration of the continuity equation. Which is del Vx over del x plus del Vy over del y is equal to 0. If you integrate both sides, all terms from 0 to delta t, del Vx over del x dy plus integral 0 delta t del Vy over del y dy is equal to 0, right? And this is, this is nothing but del Vy, right? So it's basically, So this entire thing is going to be Vy calculated at delta t minus calculated at 0, which is actually equal to Vy delta t, right? So you can write down the Vy delta t is equal to, because that's minus 0, because Vy 0 is 0, is equal to minus of this term minus integral 0 from 0 to delta t del Vx over del x dy. Correct. So let's substitute this in to the thermal energy equation, and we get the following. So we write down this, this, and this. Okay. 0 to delta t, del over del x, Vxt dy plus, well, actually, since this is minus, I just change the plus to minus. T infinity times integral 0 to delta t del Vx over del x dy is equal to alpha integral 0 to delta t del t over del y. So from here, we get integral 0 to delta t del over del x. So you have the same integral, the same del over del x, right? So you can combine them. Vx t minus Vx t infinity dy, because t infinity does not change with y, so you can take it inside. It doesn't change with x either. Is equal to alpha. Now this term is del t over del y, estimated at boundaries. You subtract, right? Del t over del y, delta t 0. So you're getting there, right? So we simplified it a lot. One question is a similar question we asked in the momentum case. Can we actually bring the derivative out of the integral? Can we bring the derivative out of the integral? Which rule did we use? Which rule from calculus did we use to do this? You remember?
Was it something like Leibniz?
Leibniz rule, exactly. So let us use Leibniz rule. Anybody who knows who is Leibniz? Who that guy is? He's both a mathematician and a philosopher. He found the calculus. He's the guy who found the calculus independent of Newton. So actually there are two guys who established the calculus Leibniz actually approached the problem in a more mathematical way. Newton actually needed to solve his equations in order to like understand how the nature works, and he was trying to find out some mathematical scheme to develop theory for gravitation and also um, laws for the moving objects, and he used it for those purposes. Independent, Leibniz just found it in a completely different context, purely in a purely mathematical intellect or interest, I would say. So that's the guy who found the calculus. And okay, so the Leibniz rule is integral, the derivative of the integral from ax to bx. It's basically the Leibniz rule is a more general form of the fundamental theorem of calculus, saying that the integral is the inverse of the derivative. But this is more than that, so you can actually make the boundaries be functions of x. So this is, Leibniz says that you can take the derivative inside, but you should have some extra correction terms. Plus f x comma b db over dx minus fx comma a dA over dx. Good. Okay. So for our case, I'm interested in this form, right? In our case, this one. And I want to take this out. I want to take this out. I want to have this one instead of this, right? So that's my objective. That's the scheme. Now, so for my case, the f xy is u, dx t infinity minus t. Ax is equal to 0. And the bx, the upper boundary, is equal to delta t. Okay. And fx comma b, okay, x comma b is equal to this term evaluated at delta t, right? That's going to be vx vx evaluated at delta t. So basically we have v infinity times t infinity minus t infinity, which is equal to 0. And dA over dx for our problem. So make this this thing makes this 0, this entire thing 0. Now let's have a look at this term, okay, in an attempt to make that 0. With the hope of the fact that it's going to be 0, dA or dx is equal to 0, correct? Because ax is 0. So this term and this term are 0 for our case. So that means I can take the derivative out of the integral with no harm, right? Thus, integral del over del x dy dx for our case. Okay, so the thermal energy equation becomes d over dx from 0 to delta t, Vx t infinity minus t dy, right? So these terms, yep, is equal to the right-hand side, which is alpha times del t over del y at y is equal to 0, right? Because this term actually, so that term becomes 0 when y is equal to delta t, because you know that the profile saturates and it doesn't change anymore. The gradient is 0 for delta t. So you can just write it at 0, but you need to subtract it, right? So there must be like a minus sign here. But I actually took it into account by just replacing the positions of the two things, right? Instead of t minus t infinity, I used t infinity minus t, so that accounts for the change in sign. Okay. So this is the energy integral equation. Analogous to von Karman equation for momentum transfer. Right? Okay. Now let's do some simplifications. Let's define theta is equal to t minus t wall divided by t infinity minus t wall. The reason is basically I want to also temper my boundary conditions. Okay. D over dx 0 del t dx instead of t infinity minus t, I'm gonna have, so okay, let's do it this way, t infinity minus t wall plus t wall, or maybe let's say minus t minus t wall. Okay, so but instead of this, we wrote down this thing. As you can see, I subtracted t wall and added t wall. I just want to make something which looks like this. Divided by t infinity minus t wall. And I'm going to divide both sides by t infinity minus t wall, so that should be okay. I added this thing extra. But I promised to divide the right-hand side as well with that term. Is equal to alpha del over del y t minus t wall divided by t infinity minus t wall. This was, as I promised, I divide by that term, and subtracting a constant number from the argument of the derivative doesn't actually harm, because the derivative of a constant is 0, so you can actually add that with no expense or cost. Okay. From here you get d over dt, d over dx, integral from 0 to delta t, Vx. This is 1 minus theta, because this thing is 1 and this thing is theta. Okay. dy is equal to alpha del theta over del y, because this entire thing is theta. Cool. Excellent. Now we have a simple equation again. By the way, this is valued at y is equal to 0, right? So it's y is equal to 0. This is y is equal to 0. Okay. Now let's assume 2 separate cases at this moment. Let us assume 2 different cases. One is nu over alpha much less than 1, and the other nu over alpha is much greater than 1. So case 1, let's pick the case 1, nu over alpha much less than 1. Okay. Meaning that delta is much less than delta t. Okay. In other words, your profiles look as follows. This is the velocity profile. And this is your temperature profile. Okay. And U, Vx. So one assumption you can make here is the following. For most of the thermal boundary region, the velocity can be approximated at constant V infinity. That's a legitimate assumption, right? Vx not scaling with V infinity, but it's almost equal to V infinity. Almost throughout the entire thermal boundary layer.